Okay, so welcome to this next video in which we are discussing the pore of the nicotinic acetylcholine receptor. Okay, so we've now discussed that the membrane-spanning alpha helix of each subunit of the nicotinic acetylcholine receptor, which is lining the pore of the nicotinic acetylcholine receptor, is this M2 alpha helix. Okay, so what I now want to discuss with you is what an alpha helix is, and we're going to actually look at the structure of these M2 alpha helices. And it's worth remembering that you have 5 of these. So if I draw each one of them, here's one alpha helix. So this is an M2 alpha helix of one of the subunits. Then we have another M2 alpha helix, then another one, okay, and then another one, and they themselves are forming this pore, so they are within these larger subunits. So let me draw their larger subunit here. So here's the larger subunit that the M2 membrane-spanning alpha helix is within, but they are what are creating this tube through which ions move. So we are now going to study these M2 alpha helices. Okay, so we'll start off with what an alpha helix actually is. So an alpha helix is a secondary protein structure. Okay, so when you make a polypeptide, which is this polymer of amino acids, okay, the primary structure of that polypeptide is what sequence of amino acids the polypeptide has. Secondary structures of the polypeptide are the way that the protein folds, but the interactions which are considered secondary interactions are those which are produced by interactions between core polypeptide structures. And let me explain what I mean by that. So, if we have our polypeptide, let's say we have our polypeptide starting here. So here's the amino terminus of our polypeptide. Okay, here is the alpha carbon, and it has a hydrogen off it, and then it will also have some R group. Okay, then we have the carboxylic acid group of this first amino acid in our polypeptide, and then we'll have the next amino acid in the polypeptide, and it's linked via this peptide link, which produces this very important amide group here. Okay, so let me circle this, because this is going to be what is solely responsible for the secondary structure. So this is what's known as an amide group. Okay, right. And then what's going to happen is the next amino acid along is going to come along. So here's our hydrogen, here's our R group, and this could be a very different R group from this one, so I'll put R prime there. And then you'll have the next this amino acid's carboxylic acid group, and it will be bound again, and this process continues on. So this is the primary structure of the amino acid. Now what can happen, basically, is that polypeptide chains, okay, if you have your polypeptide, initially maybe it will be linear like this, but what can happen is that polypeptides can assemble into spring-like structures. So imagine a spring, basically. So the linear polypeptide is the equivalent of a piece of metal, maybe like a paperclip once you've unfolded it, okay? Whereas this is like a spring, so it's a piece of metal in that spring-like structure, and this is what's known as an alpha helix. So polypeptides can wind around one another like this in an alpha helix. Now, how does this occur? What is holding this together? Well, basically, let me show you. So if this is part of this alpha helix here, so let's say this is this portion here, so I'm just drawing this line, then let's put an amino acid there, okay? So let's put, which amino acid should we put there? We'll put an amino acid here. In fact, I'll keep it general, I won't put a specific amino acid. So here comes an amino acid, okay, and it will have a carboxylic acid group coming down maybe like this, and then it will be bound to the next amino acid. So we'll continue this process on. So here comes the next bit in red, and it will loop round like that. So This is this portion. So we're just zooming in and we're seeing an individual amino acid in this alpha helix. And it will loop round. Okay, and let me draw this looping round like here. And maybe now there's another amino acid down here. Whoops. Okay, so let's draw another amino acid down here. Okay. So here's our amino acid within this polypeptide, the alpha carbon here, with an R group coming off. And here's its carboxylic acid group, and then it will continue on, and then loop round again. The thing that is holding this structure together is interactions between the carboxylic acid groups of amino acids above, in the ring above, and the hydrogen on the amino groups of the amino acids below. Okay, so what's going to happen between these two? You're going to form what's known as a hydrogen bond. Okay, so this nitrogen here is covalently bonded with this hydrogen here. Okay, so the nitrogen has provided one electron and the hydrogen has provided one electron into this bond. However, these electrons in this bond are feeling pulls, they're feeling forces. What from? Well, it's from the nuclei of both the nitrogen atom and the hydrogen atom. In the nuclei of both the nitrogen and the hydrogen atom, you have protons, which are positively charged. So the nuclei of these two atoms are positively charged, and they are pulling on the electrons. Now, the pull that the nitrogen nucleus exerts on these electrons is stronger than the pull on the hydrogen. Is stronger than the pull that the hydrogen exerts on these electrons. So there's a very fancy word for that. It's known as electronegativity. So electronegativity is the fancy name for how strongly an atom's nucleus will pull on electrons. Nitrogen, we say, has a very high electronegativity because it will pull on electrons hard, basically, with a lot of force. Whereas hydrogen has a lower electronegativity. So what's going to happen is these electrons are going to be pulled towards the nitrogen. Okay, and that's going to mean that this bond becomes polar. The hydrogen becomes slightly positively charged, and the nitrogen becomes slightly negatively charged. So this delta means just slightly, a little bit, and then positively or negatively charged. Okay, the same thing is going to happen on these carbonyl groups over here. Okay, so oxygen has a greater electronegativity than carbon. So it will pull the electrons in this double bond towards itself and give itself a partial negative charge, and the carbon will get a partial positive charge. In addition, oxygen has two lone pairs of electrons, which act as centers of negative charge. So basically you have this negatively charged species here with these centers of negative charge, and a positively charged species here. And what will happen is this positively charged hydrogen will form a nice electrostatic interaction with one of these lone pairs on the oxygen. Okay, and this interaction is what's known as a hydrogen bond, and it's the strongest form of, well, not the strongest form, but it's a very strong form of intermolecular bonding. Okay, so these interactions are what are holding alpha helices together. And you're not just going to form one of these. You know, as you continue on, you'll have another amino acid here and another amino acid here. And the amino acid here will form the same sort of thing with this amino acid down here. So you get these continual hydrogen bonds all the way around this alpha helix, which is what's holding the structure together. Okay, right. So these N2 regions here, they are alpha helices which span the membrane. Okay, let me tell you something more about them now. So, how many times do each of these alpha helices go round? How big are these alpha helices? Well, let's draw it out then. So, you start off down here. Okay, so this is the intracellular aspect of one of these M2 alpha helices. And then what happens is that you go round, okay, for the first time, and then round again, okay, and round again, okay, round again, 4 more after this, okay. Whoops, we are running out of space rapidly, this is going terribly wrong. I'm going to start this picture again. Okay, so we'll start this picture again. So there needs to be 7 of these alpha helices. So we'll put it down here. Okay, right. So 1, 2, 3, 4. So it goes around 7 times. 5, 6, 7. Okay, so that's the structure of one of these M2 alpha helices, and then this protein will go off. Okay, so this is the extracellular aspect here, the ECF, and this is the intracellular or cytoplasmic side here. Okay, and then the membrane will be in between here. Okay, and remember you'll have 5 of these. You'll have 1 here, you'll then have another one, which I'll just draw as like a cylinder, sort of here maybe. Okay, so here's another one of these M2 alpha helices here. Okay, and then you'll have another one round here maybe, and then it'll continue on, 2 more, to make a complete ring of these alpha helices that is going round. And this is what is making up the pore of the nicotinic acetylcholine receptor. Now, I just want to focus your attention on something else, which is the fact that there will be some amino acids within this alpha helix which actually do face right into the pore of the nicotinic acetylcholine receptor. Within the M2 alpha helice, these amino acids that are right at the back, they're not going to face the pore. Which ones are going to face the pore? It's going to be these amino acids that are on these loops and are right in at the center of the pore. And these are the ones which the cations are going to see as they come through. So, these amino acids have names, basically. They're so important that they've been given names. So, the amino acid down here that faces into the pore, right down here, this is known as -1 prime. Okay, then you continue on. So you'll go up 0, 2, and then the next one up here, sorry, you'll go 0, and then you'll have 1, and then 2 will be here. So 2 prime is the next amino acid which faces into the pore. So -1, then you go up to 0, 1, and then up to the second amino acid. So we're counting up basically, and 2 prime is the one that is facing into the pore. So basically you label the amino acids which face into the pore with a prime. So 0 and 1, they don't, well actually 0 does, 0 gets a prime. The reason is it's slightly in the pore, but 1 wouldn't be given a prime. So you prime the amino acids which are facing into the pore. So you then, after that, you just count. It's just a counting exercise. So you have this amino acid here which is labeled -1, 0, then 1 will be somewhere here, 2 faces into the pore, so it's called 2 prime, then 3, 4, 5, 6 is the one that next faces into the pore, so 6 prime is up here. Then you'll have 7, 8, and then 9 is the next one that faces into the pore, so it's the one up there. Okay, you'll continue counting. 10, 11, 12 is the next one that faces into the pore, so you have 12 prime. 13, 14, 15, 16 is the next one that faces into the pore, so up here is 16 prime. 17, 18, 19, 20, 20 is the one that next faces into the pore. So that's how we label up these amino acids. Now there's another important one that faces into the pore, which is right down here, which is called -5 prime. So these are going to be very important amino acids because these are the ones that on each alpha helix, each M2 alpha helix, so this is an M2 alpha helix, these are the amino acids which are actually going to face into the pore, and we'll see some examples of these amino acids in the next video.